Good morning. Sorry. The topic today then is again statistical testing, because we have to talk about the multiple testing problem that is very famous in functional neuroimaging. And we will address this by talking about multiple testing. Before we start, any questions regarding last session where we reviewed everything that we've done so far and started a little bit on statistical testing? So anything that you would like to discuss before we start? No. Good. So then we will have to today again start with statistical testing and first talk about hypotheses and tests. Briefly again about test error probabilities. And significance levels, and we will do both of this significance levels, both of this for the single test scenario, where you have one test that you're trying to evaluate. For example, you have a single t-test on a given voxel, or you have a single cluster and you want to assess whether this cluster is large enough to be declared significance based on some cluster size threshold. Single test scenario. And then we're going to talk about the same concepts in the multiple testing scenario, where you basically do a test at every voxel that you have acquired or over all the clusters that you have observed. And this is, of course, then the scenario where people would tell you you have to control for multiple testing, because if you control with only one threshold in one test and then the next test and so on, then the probability for having at least one false positive increases quite fast. But this stuff that is usually discussed there is then not that helpful to actually address what the family-wise error rate is and how it's controlled by the maximum statistics. So I will use it. Yeah, I will basically use this approach of defining these concepts, hypothesis and test error probabilities and significance levels, to introduce the family-wise error rate and how it's controlled in functional imaging, namely by using maximum statistics. So the big aim of this whole session is to understand what the family-wise error rate means, because you remember that you've seen that this is listed in the SPM table, where it says WER corrected p-value or something like this. So what is the family-wise error rate, and how is it controlled by a maximum statistic, and what this means, because if you look into how or if you start reading up on random field theory based p-value evaluation, the first thing that you will come across is this kind of somewhat esoteric concept of our Euler characteristic, and this is used to approximate the distribution of the maximum of a random field. And the question is, why do we want to do this? Why do we need this Euler characteristic? Why do we want to use the maximum of a random field? And the answer is because we want to control the family-wise error rate. And to establish all of this, we will start with the single test scenario again and go into the multiple testing scenario. And there, when we talk about the test error probabilities, introduce the family-wise error rate, and then make clear how this can be controlled using the maximum statistic. Yeah, so that's the plan. And I'm sorry, but that's how functional imaging has evolved, and this is what we need to discuss in terms of controlling the multiple testing problem in fMRI. Good. Any things you want to say in your defense? No. Good. Then let's essentially start again, but go a little bit quicker in the beginning, because we've seen some of that. So if we now start with the single test scenario again, so what you should keep in mind, in the back of your head, you should have the t-test that you did in undergrad statistic. Yeah. So think about a one-sample t-test. So you acquired some data, you compute based on the data, you compute the average and the standard deviation. You compute the t-statistic, you compare the t-statistic to some critical value, and then you either declare significance or you don't declare significance, so you reject the null hypothesis or you don't. So this is the example that you should have in the back of your head, and we are now again introduce the more general, more abstract, more mathematical framework that is used to generalize these specific example, like a one-sample t-test. So again, we start with the idea that we have a parametric statistical model where y is a random vector and y takes on n-dimensional vectors. So for example, y would be the time series of a single voxel, or for example, data from 10 participants. And the assumption is that y is distributed according to some probability distribution that is governed by some parameter, and this parameter theta is an element of a parameter space. For example, if you think about normally distributed data, then theta would be the expectation parameter and the variance parameter. Yeah, so that would be an example. So that's the basic assumption, and then we already established last time that if we talk about hypotheses in statistical testing, what we mean is that we partition the parameter space into two subsets, two disjoint subsets, theta 0 and theta 1, so that together theta 0 and theta 1 form theta, and the intersection of theta 0 and theta 1 is the empty set, so it's a partition of theta, and then we call the state that the true but unknown parameter is an element of theta 0. We call this null hypothesis, and because to always say theta in theta 0 is a little bit annoying, we also just call theta 0, so the parameter subset theta 0, the null hypothesis, and we call theta in theta 1 the alternative hypothesis. And hence theta 1, so big theta 1 is also the alternative hypothesis. And then, of course, we can think of simple examples. So, for example, if you're thinking about, again, something like you have data, so your data model is something like this. You have a normal distribution, so a multivariate normal distribution over n data points. Then your parameter could be mu, and we assume that the variance parameter is known. And then a partition of a parameter space. So parameter space in this case would be the real numbers, because mu is the only parameter, and this is a real number. Then a partition could be theta 0 is 0. So the null hypothesis is that the true but unknown parameter is 0, and the alternative hypothesis would be that it's any real value any real value but 0. Yeah? So that would be, this is what then also called a simple hypothesis. If there's only one element in one of these hypotheses, then this is called a simple hypothesis. If there are more elements in there, it's called composite hypothesis. So that's the test scenario. So again, the important thing is that null and alternative hypotheses are statements about the true but unknown parameter in relation to the subsets of parameter space. So a null hypothesis is always a statement about the value of the parameter, of a parameter of a statistic parametric model. And based on this hypothesis scenario, we then can define, actually we can also define tests without this hypothesis scenario, but we can't define test error probabilities without this scenario. So it makes sense to first establish this scenario. Then next we establish the notion of tests, and a test in all its generality is just a mapping, which I here, maybe I stopped doing this, always expressed with respect to the random variable data, is a mapping that takes a data set, so an n-dimensional vector, and maps that onto the element 0, 1. The elements of, the set of 0, 1, so one of these elements, the point here is that, like a t-test, you have the data, and in the very end you declare the significance. So you go from the data here, data space, to your final decision. And a test is this whole thing, and it's, the essence of a test is this whole thing. The 0 is the act of not rejecting the null hypothesis, so accept null hypothesis. And 1 is accept alternative hypothesis, and this is all binary, so you cannot both accept the null hypothesis and the alternative hypothesis. So that's the essence of a test. Actually, if you do a test in, for example, MATLAB, then the tests usually, these functions that are implemented in MATLAB at least, they usually actually, the basic output that they give is 0 or 1. And not some p-value or t-value or something, but just 0 and 1, so either rejection or non-rejection. And that makes sense because that's what a test essentially does. And then the tests that we are mainly familiar with, and also are mainly used in neuroimaging, are these tests that which I call, I think, standard tests. There are different names for them. Call them standard test, which comprise a test statistic, which is a mapping from, maybe I stopped this big Y now, let's see how that goes, a test statistic which maps the data into, which goes from data space to the test statistic space, which is usually, or for what we are looking at, a subset of the real numbers. So you go from an n-dimensional entity, which, for example, in fMRI can be these 400 data points, to a single number, for example, the t-value. Another single number that one often encounters in fMRI is then the cluster size. But yeah, you somehow project the data onto a lower dimensional number, which is called test statistic, and then on the test statistic you use some decision rule, delta on gamma. I don't know. You can also just write it like this: delta, which then goes from the real numbers, so from the test statistic space, to the test outcome space. And then if you concatenate these functions, you have again a test. So if you define phi as the concatenation of delta and gamma, so essentially you just apply first gamma to some data y, and then you apply delta to gamma y. Then you have the test again, and the typical procedure for doing this is based on a threshold value. So then a test looks like this, or can be written like this. So if you, or not a threshold, or a critical value, let's say you have the data outcome space, you map to the test outcome space, so rejecting or not rejecting the null hypothesis, and y gets mapped to phi y, and this is now defined as 1 if the test statistic of y is larger than some critical value, or 0 if the test statistic is lower than some critical value. Yeah. So to make this concrete in terms of the one sample t-test, the y would be a list of data, and then gamma y would be the t-statistic. So it would be, what is it, square root of n, the average of the data divided by, I will not write this out, the square, the standard deviation of the data. I think that's it. And then the decision rule, which you have here, basically here, is that you look up some critical t-value, then you reject the null hypothesis if t is larger than t critical. Yeah, so that's what you've done in undergrad statistics. I don't think that there's you should be familiar with this, because that's what you've done. It's just talking about this a little bit more abstractly, because t-tests are not the only tests that can be done. Same logic applies to f-tests, same logic applies to z-tests, same logic applies to the cluster size tests in fMRI that we will come to, and that have been the center of some debate recently. The important thing about this whole thing, or one important thing, is that the test statistic, so the gamma y is a random variable and has a probability distribution. And you know that because the t-statistic has a distribution, namely the t-distribution, and based on the distribution of the test statistic, one can then enforce certain test error probability rates. So the probabilistic nature and the probabilistic machinery in testing kicks in at the level of the test statistic, and this is also one thing that is related to that, is this notion of a rejection region, because it makes clear that how the tests behaves has a lot to do with how the test statistic behaves probabilistically. So the rejection region of a test is just that subspace or subpart or subset, I guess it's best, that subset of the test statistic outcome space for which the test rejects the null hypothesis. So that's essentially the test statistic outcome space. And yeah, these are all test statistic values such that test rejects the null. That means that essentially that the events, so if you think in terms of probabilistic events, the events, the test rejects the test statistic is in the rejection region are equivalent. So it's essentially the same event and hence equivalent. These two events have the same probabilities. Yeah, so the probability that the test statistic is in the rejection region is the same as the probability that the test rejects the null hypothesis. So if you want to visualize this and think about the t distribution again, so you will, for one sample t-test, you will usually then you will define a critical t-value, so that's your critical t-value, and you will reject whenever your observed t-value is larger than the critical t-value, so you will reject everywhere here, so that's your rejection region here, so the right and tail. And then, of course, you can get the probability for the test statistic to fall here from the t-distribution. And this probability is then the same probability as the test rejecting the null hypothesis. Yeah. So why this is important is because we will now define test error probabilities with respect to the test, so with respect to the phi, whether the phi is 1 or 0, but if you want to compute what is the probability that phi is 0 or phi is 1, you have to think about what is the probability of the test statistic to fall into the test rejection region, because that's usually where you have actually the probabilities much more readily at hand, because you get these distributions, so in this case the t-distribution, you get them by applying the formula of the test statistic to the probability, mass, or density function of the data. Yeah, I think that's briefly the review of what we did last time. And the next thing would be test error probabilities. Do you have questions about what we've now just seen? No? So this was just basically describing in somewhat abstract terms the scenario of doing a one sample t-test. And so far there is actually, it's not really clear what a good test is, because we just said a test maps data into the set 0, 1. So if you define just a test to map all observable data, all data that you can observe onto 0, it's a test. But the question is it a good test? And it's likely not a good test. So you need some criteria to construct tests and to make statements about the quality of tests, test error probabilities. And these things will also be familiar. Of course, this is then based on this 2x2 setting, where you can have the case that the null hypothesis is true. So theta is in theta 0, or theta is in theta 1, so the alternative hypothesis is true, and then you can have the two outcomes that phi y is 0, so the null hypothesis is accepted, the alternative rejected, or phi y equals 1, so the null hypothesis is rejected. And this is of course something that you've seen previously in undergrad statistics. And then of course there are two cases where things are fine. So if the null hypothesis is true and the null hypothesis is accepted, then everything is fine. So that's a correct decision. Same if the alternative hypothesis is true and the test rejects the null hypothesis, then it's also a correct decision. And then you can have these two errors. So you can reject the null hypothesis if it's in fact true. For some reasons this is called type 1 error. And you cannot reject the null hypothesis or accept the null hypothesis if the alternative is true. And this is called the type 2 error. So these are the single test scenario errors. Errors and correct decisions. And the idea of tests then is to construct tests in a way that you somehow have some guarantees on the probabilities of doing test errors. So that means if you use these tests again and again and again, you want to make sure that if you on average control the error rates. And then the interesting thing that has happened in science is that people are more worried about type 1 errors than about type 2 errors. So type 1 error is then usually controlled first. So you set up a procedure that keeps your type 1 error at a given rate, and then as a second thing, people sometimes worry about type 2 errors, but this is then usually done in the context of keeping the type 1 error rate at a given level and controlling the type 2 error second by, for example, increasing the sample size. So that then goes into this whole business of power. We will not discuss power because that would be too much. You can read about fMRI power in our recent preprint where we discuss a lot about power, and that especially in multiple testing you should be a little bit careful about what kind of power you're actually talking about. But yeah, we will not deal with that here. So the important thing is that if you have these errors and you have this idea that if you repeat the test, the similar procedure under the under similar assumptions about the data distribution, that you want to, in a way, minimize your errors. And to this end, one then defines the test error probabilities. And the first test error probability that we are going to define we call alpha. And that's the probability under, and this should mean null hypothesis. So under the probability distribution of the data under the null hypothesis, meaning that the parameter of the probabilistic model is an element of the null hypothesis. Under this assumption that the test comes out 1. So reject the test if, so that's the probability to reject the null hypothesis if theta 0 is true. Yeah. But it's so what I'm trying to stress here is that a type 1 error and the probability for type 1 error are two different things. Type 1 error is just that you reject the null hypothesis if it's in fact true. The test error probability for that is the probability to reject the null hypothesis if it's in fact true, and this is called alpha, and alpha is also called the size of a test. And again, you get these probabilities by looking at the test statistic. So if you have because the probability for the test statistic to be in the rejection region and the probability for the test to reject the null hypothesis are the same thing. So if you want to compute this probability based on the data distribution, you can look towards the test statistic. So that's the size or type 1 error rate. Let's call it type 1 error rate also. Size. So a rate is a probability. Yeah? And then it's relatively straightforward to define the complementary probability. So if the null hypothesis holds, the test can of course also be 0. And this of course we can, because it's the complementary event, so either the test is 0 or 1. So this is then 1 minus alpha. So if we compute this, can compute the size, we can easily compute the probability that the test is test outcome is 0 under the null hypothesis. This is called the specificity. It's usually not discussed much. And then there's another probability, and now looking under the assumption that the alternative hypothesis holds, there is of course the probability that the test doesn't reject the null hypothesis, so accepts the null hypothesis. That's the probability of a type 2 error. Which doesn't have a name for some reason. But its complementary probability, namely the probability under P, under the alternative hypothesis that the test does the correct thing, that's called the power. Yeah, so test error rates are actually only this one and this one, because these are errors. Of course, the specificity and the power are not error probabilities, but actually correct decision probabilities. We can actually stress that also. Yeah. So that's the nomenclature here. The important thing, actually, for our most important thing, will be the size. Yeah? So the type 1 error rate, so the probability for type 1 error, meaning the probability for the test to reject the null hypothesis if the null hypothesis is in fact true. This probability will be for everything that we do here in this in the remainder of this course will be the important thing. Yeah. Questions about these test error probabilities?
Just about the nomenclature, I remember that there was probability of type 2 error, and we always learned that 1 minus beta equals power.
Yeah, I know. The reason I'm doing that differently is because in mathematical statistics there's also the notion of the power function or the test quality function, and this is usually also called beta, and this then is a function of the parameter and corresponds to the size if the null hypothesis, if theta is in the null hypothesis, and corresponds to power if theta is in the alternative hypothesis. So that's why I use beta here, because in the context of actually computing power for example, for fMRI, you need this test quality function, which is in mathematical statistics not referred to as 1 minus beta, but as beta. So that's why I'm doing it differently. Actually, I also comment on this a little bit in the script, because if you go through the literature, you find that in mathematical statistics they call this test quality function beta, which relates to power, and then it's just easier this way around. So we will not discuss power. Again, read our paper if you are more interested in power. Good. So then before the break, I think we should briefly talk about significance levels, because so far we've talked about the test error probability. So that's again theta, which is theta alpha, which is a value between 0 and 1. That's the probability for the test to come out 1 under the assumption that the null hypothesis is true. So that's the probability for type 1 error. And now we are introducing the notion of a significance level, which is not the same as a test error probability, not necessarily. Let's define it. Phi is of significance level alpha prime. So significance level will always have this prime there if its size alpha is smaller or equal to alpha prime. So alpha prime. So the reason why this often causes confusion is because you are mainly familiar with the t-test, which is an exact test. So an exact test is a test with a significance level alpha prime, which equals the size. So you are in the case that, well, let's do the other way around, that alpha equals alpha prime. So if you say you want to do a 0.05 significance level test using the t-test, it's an exact test because the test error probability of the t-test, if you use a significance level of 0.05, is exactly 0.05. However, that doesn't need to be the case, so you can have what is referred to as a conservative test. Which is a test for which the actual error probability, type 1 error probability rate, alpha, is smaller than the significance level. Yeah? So people sometimes say they use a conservative test of 0.001. That's just a test with a low significance value. A conservative test is a test where you choose a specific significance level, for example 0.05. But if you choose that in your construction of the test, the actual error rate that you then get is lower. So for example 0.028 or something like that. So that would be a conservative test. And in this sense, actually using Bonferroni correction in neuroimaging over voxels is conservative. It's not conservative because it has a very low significance level, but it's conservative because if you specify a Bonferroni value for testing, then the actual error probability is lower than what you have specified. The last thing is the notion of a liberal test, which is not even of significance level alpha prime, so that would be if alpha, so if the test error probability is actually larger than your significance level. But that's not even a test of significance level alpha prime, so it's not really that interesting. Yeah, so the main thing that you, where this kicks in, is that you should always remember that if you specify a significance level, so you choose alpha prime, then what you do is you look up, for example, a critical t-value, and then your decision is based on your observed t-value being larger than your critical t-value. Yeah? And so if, for example, this translation of a significance level into critical value is not optimal or something, and you then do this, then the test, the probability for phi 0, for phi being 1 under the null hypothesis may still be not the same as the significance level. No? So that's, which doesn't happen actually if you look at the one-sample t-test. This is why this difference between significance level and size might confuse you. But if you look, it actually can also happen there. For example, if you have think about the idea that you have, that if you look up the corresponding t-value, so if you think, for example, of something like this, so let's say you have a table, and the table says something like this, so 0.01, let's do it differently. So you have a very low resolution table for your t-statistic. So here you have your alpha prime, and then you can look up the test statistic. And that of course will also depend on the degrees of freedom, but let's say here you have something like 2.3, here you have something like 0.01, 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 here you have 2.1 to make it simple. Here you have 1.9. Now you want to have a significance level of alpha prime, so you want the test size to be, so let's say you have alpha prime being 0.05, and so you want to make sure that the test size, so the actual error rate, is smaller or equal to alpha prime. Now you can, we could interpolate, but say you want to stick to the table, so then you would not, of course, choose this critical t-value here, because then you would already know that the size is larger, but you would choose this, where actually we could also, so here you can think whether this is actually a significance level or alpha. You can also call that alpha. So you would choose 0.04. Then you would still have a significance level of 0.05, but you already know that your test size will be 0.04, because you will use this t-value as the critical value, and then your significance level and your size are different, because your table for looking up the critical value is a little bit coarse, and you don't want to use things here where you have a larger test size. So it's a little bit artificial, but it's then not that artificial if you, so because it's always the question how you translate your significance level, what you would like to have into your critical value. And for example, in fMRI, where you for example, have discrete cluster sizes, or in the set level test, discrete number of tests, then it's quite easy that if you use your critical value one higher, so for example, for the set level test, you include one more cluster, that then the probability jumps actually quite significantly over the 0.05. So for example, go from the 0.3 to 0.7 only by including one discrete more cluster, and then of course your significance level and your test size will be different. Good. Questions? Have a look at the single observation z-test, which also shows you a little bit how these things then go into the construction of actual tests. But I want to then in the next hour discuss this again, but then in the multiple testing scenario. Yeah? Good. Then let's have a break and continue at 9.